one other topic that is usually misunderstood is intermediate value theorem. So the idea is very simple. If you have a continuous function, but you don't know its graph, you cannot see its graph. But what you can see is that at point A, the graph, let's say, is below the x-axis. And at point B, the graph is above the x-axis. Now, no matter how you connect those 2 points by an invisible wire, the curve has to cross the x-axis at least once. So here is how this idea may be applied. So suppose that we look at the equation x to the power of 4 plus x minus 3, and we want to solve when this is equal to 0. Suppose that we test this function. Let's call this function p of x. Suppose we plug in the number 1. So that would be 1 plus 1 minus 3. Well, clearly a number less than 0. Now let's test it at another value. Let's say at the value 2. So then what you have is 2 to the power of 4 plus 2 minus 3. We can evaluate it, but the point is that, well, it's 15, but the point is really that it's clear that this number is bigger than 0. So the conclusion is, because p is a continuous function, it's a polynomial, because p is continuous, p of x equal to 0 for some x between 1 and 2. And that follows from the intermediate value theorem. Because again, without drawing the graph of x to the 4 plus x minus 3, we just observe that the graph is a graph of a polynomial, so therefore a graph that is a continuous curve, something like over there. So we observe that at the point 1, we are less than 0. The graph dips below 0. At the point 2, the graph is above 0. So somewhere in between 1 and 2, the graph had to cross the x-axis. Let's consider a few more problems. Let's suppose now that we have the equation sine of x equal to x squared minus x. So we can translate this equation to one where we compare to 0. So we have here x squared minus x minus sine x equal to 0. It's usually convenient to translate to compare to 0. So now this function here, let's call it f of x. F of x is continuous. So let's check it at a few values. So let's suppose that we check it at the value 1. F of 1 is going to be 1 squared minus 1 minus sine of 1, where 1 here means 1 radian. Now 1 radian is smaller than pi over 2, but bigger than 0. So you can clearly see that this number here, 1 minus 1 is 0. This here is smaller than 0. So f of 1 is smaller than 0. Let's see what happens at f of 2. If I put f of 2, that would be 2 squared minus 2 minus sine of 2. In other words, sine of 2 radians. So that will be bigger than 2 squared minus 2 minus 1, because subtracting sine of 2 is At the very worst, actually subtracting 1. Sine never exceeds 1. So what is this? This number is 4 minus 2, which is 2, minus 1. This is 1. So that is bigger than 0. So the conclusion that we can draw here is that sine of some number c is equal to c squared minus c, where c is bigger than 1 and less than 2. All right, let's look at another example, example 3. Suppose that we consider e to the x equal to 3 minus 2 to the x, and we want to show that this equation has solution between 0 and 1. So try it yourself before proceeding. So one thing we can do is we can define a function f of x to be e to the x minus 3 plus 2x. And we want to solve when this is equal to 0. When is it equal to 0? So we can try, first of all, selecting f of 0 and see what we get. So we get e to the power of 0 minus 3 plus 2 times 0. Now e to the power of 0 is simply 1. So that is 1 minus 3, which is clearly less than 0. Now let's consider what is f of 1. That's going to be e to the power of 1 minus 3 plus 2. So that's just e to the power of 1 minus 1. Now e is bigger than 2.71. So 2.71 minus 1 is bigger than 0. So we see that the graph of this function of f of x, which is a continuous function, is below 0 at 0 and above 0 at 1. Therefore, there must be a point C that solves this equation. By intermediate value theorem, we get that f of some c, for at least one c, is equal to 0. So in other words, e to the power of c is the same as 3 minus 2c. And c is bigger than 0, less than 1. All right, those are easy examples. Let's try something a little bit more difficult. Consider a more abstract problem. Suppose that you're given a function f from the closed interval 0, 1 into the open interval 0, 1. And this function is continuous. So what does this mean? It means that this function takes input in between 0 and 1, and outputs are bigger than 0, smaller than 1. So we have f of x is always less than 1, always bigger than 0. Show that f of c is equal to c for some c between 0 and 1. All right, so to understand this question, let's try to draw what we can. We are interested in the equation f of x equal to x. naturally I'm not claiming that the function f is the identity function. I'm not claiming every number is mapped to just itself. But we're searching for what you call a fixed point. We're searching for what values are not changed by this function. What values are not changed by this function at all? For example, you might well, I'll show you an example after this abstract presentation. We know nothing at all about f, except that the function is continuous. So let's try to draw what we know. So here is the line y equals x. Now, by the definition of this function, for all values between 0 and 1, here is the x value 0, here is the x value 1, here is y value 0, y value 1. For all those values, first at 0, the function f of 0 has to be bigger than 0. So it's somewhere here. And f of 1 has to be smaller than 1. So it seems natural that if the curve is continuous, it will have to somehow cross and produce a point that is unchanged. So on the actual curve of f of x and on the curve y equals x, we have an intersection. So how do we use the intermediate value theorem to prove it? So what we can do is we define, as before, we move everything into one side. We move the equation and write f of x minus x. So we define g of x equal to f of x minus x. Now, we know that g of 0 is equal to f of 0 minus 0, which is equal to simply f of 0, which is bigger than 0. On the other hand, we know that g of 1, which is equal to f of 1 minus 1, is smaller than 1 minus 1, which is equal to 0. So g is continuous. By intermediate value theorem, g of c is equal to 0 for some c bigger than 0 less than 1, and we're done. Whenever g is equal to 0, that means that 0 g of c is f of c minus c. So that means that f of c is equal to c. Now, an example of such a function of what we just said is, suppose that our f of x was something like cosine of 1 over 1 plus x squared. So this looks like a fairly complicated function. But what we know is that this function f of x is always less than 1 and always bigger than 0 if x is between 0 and 1. So what we have just effectively shown is that for some x, cosine of 1 over 1 plus x squared is really not doing anything to that x. It's just giving you back that same input. That's what we have shown in general. All right, let's see if you understand this problem. Let's change the definition slightly, or the instruction slightly, and require that the function is still as before, it's continuous. That means that f of x is less than 1 and bigger than 1, and it's defined as before on the interval from 0 to 1. Now you want to show, use the intermediate value theorem to show that f of x equal to x squared has a solution in the interval 0, 1. In other words, what do you want to show? You want to show that this function, whatever it may be cosine of 1 over 1 plus x squared, squares one of the inputs. So there is one number, I'm not quite sure what it is, but one number between 0 and 1 that will be squared by this function, even though that the function is not square. Again, we can understand it visually by drawing the box. Before proceeding, press pause and try to see what is the corresponding box drawing. So here is x equal to 0, x equal to 1, y equals 0, y equal 1. The graph of f of x is not known to me. The function is continuous. All I know is that the graph is some uninterrupted, non-turn apart curve. I know though that what's the graph of x squared. The graph of x squared will look like a parabola. This is y equals x squared. So I can draw it because I have information about it. What do I know about this function? I know that this function at 0 is somewhere bigger than 0 and at 1 somewhere less than 1. So I know that the actual drawing of f of x must be some continuous curve connecting those two yellow points. However you try to connect those 2 points, it seems obvious that at least in one place, for some value of c, there will be an intersection. So intuitively, it is clear. Again, how do we proceed to use the intermediate value theorem? This equation is the same as the equation f of x minus x squared equals 0. So we can compare this to 0. So we define the function g of x to be f of x minus x squared. And this function is continuous. Continuous on the interval from 0 to 1. Now we observe that g of 0 is equal to f of 0 minus 0 squared, which is f of 0, which is bigger than 0. We also observe that g of 1 is f of 1 minus 1 squared, which is equal to, well, which is smaller than 1. F of 1 is smaller than 1, minus 1 squared. So that is smaller than 0. So by intermediate value theorem, we have that g of some c is equal to 0, which is equivalent to saying that f of some c is c squared. So some number is indeed squared.